Welcome to our lecture video in fluid mechanics and under the topic gravity dams. Now in this video, we will solve the 4 sample problems in our handout. And here is the sample number 1. We have a rectangular dam having a width of 10 meters and height of 24 meters and has a depth of 18 meters depth of water on one side. If the coefficient of friction is 0.85 and the gamma c or the specific weight of the concrete is 24,000 Newton per cubic meter, determine letter A, hydrostatic force acting on the wall, and B, factor of safety against sliding, and C, factor of safety against overturning. So the gravity dam here has a width of 10 meters, height of 24 meters, and depth of 18 meters for the water. So we have here our rectangular gravity dam. Okay. So it's asking for the hydrostatic force acting on the wall. So the hydrostatic force that is acting on this wall, so here, which is presented by uniformly varying force, right? So as you go deeper, the stronger is the pressure of water. So if we solve for the hydrostatic force acting on the wall, so this is our hydrostatic force. Hydrostatic force F. So how do we solve that? Letter A, F hydrostatic force is equal to gamma of the liquid. So what we have here is water. So this is water surface here, and our gamma is, our unit weight is for water, and then multiplied with HC. Why? Because if our eyesight is at this portion here, we will generate a projected area of a rectangle. So there. And the center of gravity is located here, CG. And this is the HC. So our HC is the depth from the water surface up to the center of gravity. And then multiplied with the area of the projected area that is wet by the water. So this is now equal to gamma of water 9.81. HC is 18 divided by 2, and the area is, that will be 10, that would be, if it's not mentioned, if the width of this projected area is not mentioned, we will consider per 1 meter width. Okay, so 1 meter. So this is 18 by 1. So that is equal to 1589. So 1589.22 kilonewton. Okay, so we'll put it here. So that's the answer for letter A. Let's go for letter B. It says there factor of safety against sliding. So this is the formula for the hydrostatic force acting on the wall, and for the factor of safety against sliding, that is equal to Fs is equal to mu, or the coefficient of friction, and then the RV, the vertical reaction, and then the RH, the horizontal reaction. So this is the formula. So this is the formula, for the factor of safety against sliding. Okay. So we have here already the force H. So this force here acting on the wall is actually the FH. So what we need next is the RV, the vertical reaction, and we can find that by the weight of the dam, W. So that is, how do we compute for weight? That is gamma volume, right? Gamma of the concrete, then the volume. So that's the formula for the weight. So that is equal to gamma of concrete, that is 24,000 or 24 kilonewton per cubic meter, and then the volume, which is 10 meters by 24 meters by 1 meter. So we will consider per 1 meter width. So how much is the weight? So weight now is 5,760 kilonewton. Therefore, we now have factor of safety against sliding equals the mu. The mu here, or coefficient of friction, is given as 0.85. So that is 0.85 times the RV, that is the weight. So 5,760 all over the RH, or that is the F. So 1,589.22. So the factor of safety is unitless, and the answer here is 3.08. Okay? So that's for the factor of safety against sliding. Let's go to letter C, factor of safety against overturning. So FSO is equal to the righting moment over the overturning moment. So this is the formula for factor of safety against overturning. Now let's define them again. So remember that for righting moment, so this involves the forces from the word right or righting, to correct, right? To make it erect, to make it stable. So that is the righting moment. Any force that makes it in a correct position, those are the righting forces. This is the overturning moment. This involves the overturning forces. So what are those? Those are the destructive ones that tends to destroy the structure. So in this figure, which is the righting moment? So the righting moment here will be the weight of the dam, which is the overturning moment, or the force that tends to overturn or to make the structure unstable or to destroy it. That is the force of the water. So the tendency here is, if there is too much force of the water here, the tendency will, this dam will topple down. So it will have this scenario. Okay. So since it has this kind of scenario, we will have the rotation here at this point. Okay, so this is our rotation point. Okay, so this is the failure due to force on hydrostatic force acting on its side. Now to correct this failure, so we have the righting force, the righting moment, we have the weight here in order to make it erect, right? So we now have, okay, so we have our righting moment. So we have the summation of moment at 0. So here is our point 0. This is our, there you go, OM, overturning, and this is our righting moment. Sorry, it's this different here. The righting moment is RM. Okay, so let's have the summation of moment at O is equal to 0. So righting moment is equal to the weight. The weight times its distance from O. So this is the x distance. Then we also need to find this one here, the distance from O to the force H. So weight x is 5,760 kilonewton times, what is x here? It is equal to 10 divided by 2. So that is equal to 28,800 kilonewton meter. Overturning moment, that is the force H times y. So force H times y. Force H is 1589.22 kilonewton multiplied with y. Y here is H divided by 3. So H divided by 3, that is 18 divided by 3. So OM now is equal to 9,535.32 kilonewton meter. Therefore, we now have factor of safety against overturning equals 28,800 all over 9,535.32. So the answer here is 3.02 and it is unitless. Okay, so that's for example number 1. Okay, now let's go to example number 2. So we have here a dam, 4 meters on top, 18 meters at the bottom, and 24 meter high. So this is a trapezoidal dam, 4 meters on top, 18 meters at the bottom, and it is 24 meters high. It has water 20 meters deep acting on the vertical side. Assume the weight of masonry to be 24,000 Newton per cubic meter. Compute letter A, factor of safety against overturning, B, the maximum stress, and C, the minimum stress. Okay, so this is the trapezoidal dam. So the water is acting on the vertical side. So this vertical side here. So it says there water. So this is water surface. Now, it says here compute for factor of safety against overturning for letter E. So FSO is righting moment over overturning moment, right? So our righting moment here is what? The weight of the gravity dam. Okay, so it's weight. So this is the weight 1. Then this should be the weight 2. Okay. And nothing else. How about the overturning forces? We have the force of water here. So the force of water, F. Okay. Since we're dealing with the distance, so this becomes your becomes the x1, say x1. This becomes x2. So this is x sub 1, and then this is x sub 2. And then this one here will be y. This y, or that is 20 over 3. Okay. So let's compute them. How about the force first? FH. This is FH. Is gamma of water times the HC and area. So that is 9.81 kilonewton per cubic meter. HC is from the water surface to the center of gravity. So this is our projected area for the FH. Okay, so this is our center of gravity. And this is HC. So HC so meron tayong HC, we have here 20 divided by 2. Then area 20 by 1. So since hindi not mentioned for the width, so we will use 1 meter width. So 1 meter. So 9.81 times 20 divided by 10 times, it is 1962. 1962 kilonewton. Okay, so that is FH. Now let's go to the weight. Weight 1 first. So weight here is gamma volume, gamma C volume. So gamma C is 24 kilonewton per cubic meter. For weight 1, we have here a rectangular area, so that is 4 times 24 times 1. So that is equal to 2,304 kilonewton. Then we have weight 2, that is 24 kilonewton per cubic meter. And then the volume here is 1/2 base. So our base is 18 minus 4 times 24 times 1. And that is equal to 4,032 kilonewton. For x1, so here our distances, so x1 is 4 divided by 2 plus, or 18, or that is 18 minus 4 divided by 2. So we have there 16 meters, and then x2 is 2/3 of 18 minus 4. That is 9.33 meters. Now we have our RM, writing moment. So our writing moment is the weight 1 times x1 plus weight 2 x2. So we now have here 2,304 times 16 plus 4,032 times 9.33. So we have RM equals to 74,842.56 kilonewton meter. Now let's go to the overturning. So our overturning is the horizontal force water. So OM is equal to FH times Y. So FH is 1962 kilonewton times the 20/3 here. 20 meter divided by 3. 20 meters divided by 3. So 1962 times 20, 13,080 kilonewton meter. Therefore, we now have our FSO, factor of safety against overturning, equals the writing moment, 74,482.56 divided by 13,080 equals 74. That is 5.694 So, unitless. So, 5.694. And that is for letter A. How about B? Maximum stress. So, how do we determine the maximum stress? But now, to compute for the maximum stress, we need first to determine, so, where is the location of the RV? The, what do you mean by RV? The vertical reaction. So our vertical reaction will be located here. That's the opposite of the weights. So RV. Now the question here is, what is the value of X bar? So X bar. Okay. So let's compute for X bar here. Now the formula for X bar, so X bar is equal to summation of Rm minus summation of OM all over RV. This is one of the formulas. There we go. Whereas RV, so RV is, we already have RM and OM, right? So we need to find RV. RV is the weight 1 plus weight 2 . Let's put it here. That is equal to 2304 plus or plus 40 32. So RV is 6336 kilonewton. Okay. Then we will input that now here. RM OM 74,842.56 minus our OM of 13,080 divided by the RV of 6336. So bar X is now equal to 9.69. So 9.69. Okay. So means so this is the base of the dam. So this is the base of our trapezoidal dam, that is 18 meters at the bottom. So the bar X is located 9.89. So here, around here. That means if you divide it into 3, therefore bar X is equal to 9.69 meters. Or you can also use the formula, the eccentricity equals the base divided by 2 minus bar X, and absolute value, so this is 18 over 2 minus 9.69, absolute value. The answer here is 0.69. So since this RV, this is actually the RV, since RV is within the middle third, or that it is or E is less than B over 6, or you can see here that 0.69 is less than 18 divided by 6. So what is 18 divided by 6? It's 3. So it's greater here and lesser here. So since that is the condition, we will use now the formula for maximum stress and minimum stress. S max. S max is equal to RB over B times 1 plus 6E over B. That is the maximum stress. How about minimum stress? For the minimum stress, we change this into minus. Okay? So this is our formula for maximum and minimum stress. So S max is equal to RB, a while ago it's 6336 divided by our base is 18. Right? Times 1 plus 6 times eccentricity of 0.69 divided by the B of 18. Therefore, S max is equal to 432.96 kilonewton. kPa, should say kPa. The unit here is kilopascal. Next, we have S minimum, 6336 divided by 18. 1 minus 6 times 0.69 all over 18. So what is our S minimum? It's 271.04 kilopascal. Okay, so that's for number 2. Okay, so that's for number 2. Screenshot. So let's go to number 3. A triangular dam is 30 meters high. Water is 25 meters deep on the vertical upstream face of the horizontal base. If unit weight of concrete is 23.5 kilonewton per cubic meter, determine A, the minimum width of the base that the resultant force falls within the middle thirds. Neglect the hydrostatic uplift. B, the minimum coefficient of friction to prevent sliding. And C, shearing stress at the depth of 10 meters above the horizontal base. Okay, so we have a triangular dam, 30 meters high. And then its water is 25 meters deep on the vertical upstream face. So this is our triangular dam of 30 meters high. This is 30 meters high. The water is 25 meters high. So water, says there water. So we have the water surface there. Then given the weight of concrete is again 23.5 kilonewton per cubic meter. So what is the minimum width of the base that the resultant force falls? See there, the resultant force falls within the middle thirds. Neglect the hydrostatic uplift. So middle thirds. No given value for base. There's no given value for base. But we will divide the base into thirds. So into thirds. So this is our B over 3. So this is B over 3, B over 3, and then this B over 3. Okay, so those are the middle. And the middle third here is this one. It's the middle third. Now it's looking for the minimum width the minimum width of the base, that the resultant force falls within the middle thirds. So to look for the minimum width of the base, we will place the resultant on two places. So we can place it at here. So this is our first scenario. Our RV is located X bar 1, and so RV, and then our second scenario is this one here. So this is the middle third it's talking about. So the resultant force falls within the middle thirds. Now that means this is the extreme boundary for the resultant force, here and here, extreme boundary, and then the rest here, right? So this is RV with distance X bar 2. Okay, so what's the difference between this X1 and X2? This is B over 3 and this is 2B over 3. Right? Then we can now compute for X bar by the formula summation of RM minus summation of OM all over RV. So we will solve first the value for FH, the value for weight, and the value of weight. So this is X distance. This X distance here is same, 2/3 of the base. Then this one here is Y, or that is 1/3 of 25. Is 1/3 of 25. That is 25 over 3. Okay, so FH. FH is equal to gamma of water, HCA. So that is equal to 9.81 times HC, this one here, 1/2 of the weight of the water, 25 divided by 2. And then the area, projected area, so this is now the projected area, CG. This is 1 meter width and that is 25. So the area is 25 by 1. So FH now is equal to 65.625 kilonewton. How about the weight? Weight is gamma C, volume. So gamma C here is 23.5. So that is 23.5 kilonewton per cubic meter. And then the volume is 1/2 the base times the height. So that is equal to 352.5 B. So let's compute now for the OM. The overturning moment, obviously here, is the F, value of F. So FH, Y, and that is equal to 65.625 times Y of 25 divided by 3. So that is equal to 25,546.875 kilonewton meter. Then we have the writing moment is equal to Wx, or the weight, times the x. There you go. So 352 for the W, right? So 352.5 B times the x here is 2/3 of B. So what's the answer here? For RM, writing moment. So that is 235 B squared. Okay, and then RB is simply the weight. Okay, now let's compute for the value of B at the two conditions, considering condition number 1 and then considering condition number 2. So we have here at x bar B over 3. So under this, on the formula, we have, so x bar is B over 3 RM. So we have RM of 235 B squared minus the OM is 25,546.875 divided by 3. Oh no, divided by the RB. So say RB or W, which is, so RB or W, which is 352. So 352.5 B. Okay, so let's have the value here. So alpha x over 3, that is alpha equals 235 alpha x squared minus 25,546.875 all over 352.5 alpha x. Okay, and shift solve. So x is equal to, or B is equal to 14.75. So B is equal to 14.75 meters. How about at the other condition? So our other condition here is if RB is in this position. So if RB is 2B over 3. So that means 2B over 3. We'll just copy what happened here, right? So 235B squared minus 25,546.875 all over 352.5 B. So 2, shift solve. So negative value. Therefore, so we're not going to use this condition. Therefore, therefore B is equal to 14.75 meters. So this is the what? The minimum width of the base that the resultant force falls within the middle thirds. Minimum. How about B? Minimum coefficient of friction to prevent sliding. So letter B. So minimum coefficient of friction to prevent sliding, Fs, is equal to mu Rv over Rh. Okay? So our Rh is the F, right? This is our F. So for minimum coefficient, Fs is equal to 1. Therefore, from the formula we have here 1 equals mu, then our Rb is, a while ago, where is our Rb? Is the weight. Here, this is our weight. 352.5B. So 352.5B. Our B is 14.75 all over RH, which is our F, 3065.625. So mu now is equal to, okay, so that is 0.59. So letter C, shearing stress at the depth of 10 meters above the horizontal base. So shearing stress, oops, so we don't have the, okay. So for letter C, oops, so we have here the dam, okay? So it says there, shearing stress at the depth of 10 meters above the horizontal base. So our horizontal base here, okay, so it says there that, shearing stress at the depth of 10 meters above the horizontal base. 10 meters above the horizontal base. So there will be a shearing here. So shearing at this point here. So that is 10 meters. Oops. So 10 meters above the horizontal base, and then this is 30 meters, remember, and then we have here 25 meters, minus 10, so we have here 15 meters, and this is 5 meters. Okay, so let's compute for the shear stress, shearing stress. Okay, so the tendency here is that because we're talking about the shearing stress, it means that there will be a failure at this point. So let's put here X for this distance here. There will be a failure wherein this force, so a certain force here, the hydrostatic force here, will be so strong, okay? The force here for the shearing is so strong to the point that the failure becomes like this. So there will be a crack there, and there is a sliding of the, so the structure will slide. The sliding here is like this. So if there is a sliding of the structure like that, the failure at this portion here becomes the shearing area. So let's draw that shearing area. It's oops. So this is the shearing area. This is the X, This is the 1 meter, right, width. Okay. And the formula for the shearing stress is, so shearing stress represented by tau. Tau is equal to F, shearing force all over the shear area. Okay, the shearing force and then the shear area. So this is 14.75, just as we were able to get. So by ratio and proportion, we have here x all over 5 plus 15. Triangle here. Equals the base of 14.75 over 30. Therefore, our value of x here is 9.83. 83 meters. Therefore, area or shearing area is equal to 9.83 times 1. And that is 9.83 square meters. And the force, shearing force, is gamma of water, HCA. And our projected area here is here, from the point of failure up to the water surface. So there. So this is now our center of gravity, CG. Right. Therefore, our area now, okay, so gamma of water is 9.81. Our HC is 15 divided by 2. Then the area is 15 times 1. So this is 1 meter width. So that is now equal to 1,103.625 kilonewton. Therefore, we now have the shearing stress is equal to 1103.625 divided by the shearing area of 9.83, and that is equal to 112.27 kilonewton square meter, or that is 112.27 kilopascal. Okay, so that's for number 3. Last, let's have number 4. Find the total vertical reaction at the bottom of a masonry dam from the cross-section shown. The intensity of the hydrostatic uplift varies uniformly from a 20% of the full hydrostatic pressure at the heel to 0 at the toe. Gamma of concrete is 23.5 kilonewton per cubic meter. So this is the toe. This is our toe and this is our heel. Okay, so why? Because the tendency of failure here, the scenario here will be like this. Oops. So there will be a rotation at this portion here. Okay, so that becomes your toe. So what are the forces that we can see here from this structure? We have the weight. So let's divide it into 2. So this is our weight. So W1, then this is W2. So this is W2. Then we have the hydrostatic force, of course, the hydrostatic force here, FH. And then we have the uplift force. This is there, the intensity of the hydrostatic uplift varies uniformly from a 20% of the full hydrostatic pressure at the heel. So we have an uplift force here. Oops, let's use blue. Okay. the heel and then 0 at the toe. So this is the pressure here is equal to 0.2 or 20% of the full hydrostatic pressure. So 0.2 or 20% of gamma H. So this is our H here, 8 meters. Then gamma of water, because we have here water. Okay. And then another thing to consider is this portion here. Okay. There is an effect whenever the bottom, so as you can see here, this is the bottom. The bottom is exposed to the liquid. If that happens, there exists another force that we call the vertical force, FB, or the RB. You can call that also the RB. Okay? Due to water. But because since the problem is looking for the total vertical reaction, therefore we will name this as force vertical due to water. Okay? So uplift force, and uplift force here, U. Let's name that as U. Okay, so I think we are now complete here. So all we need to do is the summation of forces. Vertical is equal to 0, positive upward. We have RB is equal to, or RB minus weight 1 minus weight 2 plus the uplift force plus the force vertical, that is equal to 0. So first we have the weight 1. Weight 1, of course, we have gamma concrete volume. So gamma of concrete is 23.5 times the volume of 2 by 1 and say 1 meter. So that is 47 kilonewton. Weight 2 is gamma C, 23.5. The volume is 1/2 base times the height of 8 meters and the width of 1 meter. That is 564 kilonewton. And then the uplift force. How do you compute the uplift force? The uplift force is like this. So it's a prism, rectangular prism. So how do you compute now rectangular prism? The volume. So this is P. The height here is P. The width is 6 meters, and then the thickness here is, or the width here is 1 meter. So uplift force is equal to 1/2 base times height, that is the P, 0.2 times 9.81 times 8. Then the 1 meter width, that is 47.088 kilonewton. Then finally we have FV. FV now is equal to the gamma of water and then volume. So gamma of water is 9.81. The volume here is 2 by 1 by 1. Therefore, this is 19.62 kilonewton. Now, if we add, put it in the formula or in the equation above, RV now is equal to, so RV minus 47 minus 564, then plus 47.088 plus 19.62 is equal to 0. So RB is equal to 544.29 kilonewton. Okay, so that's number 4. Okay, so number 4. Okay, so that's all for this video.